Hello everyone, today we'll talk about the problem find the safest path in a grid. We're given a grid containing zeros and ones. Zeros are free cells and ones are thieves that we want to avoid. We want to get from the upper left corner to the lower right corner. And not only do we want to avoid cells with ones in them, we want to stay as far away as possible from those cells for our whole path. More formally, we'll calculate the distance between cells using the Manhattan metric. So a distance from, for instance, this cell to this cell is how many steps going up, down, left, right we have to make to get from one to the other. So for instance, we can go here, and then here, and then here. So the Manhattan distance is 3. So that's how we calculate distances. And we want to consider the minimum Manhattan distance from any cell of the path. So the cell that is the closest to one of the thieves, and want to make sure that this number is maximal. So for instance, if it's possible to create a path that never gets closer than distance 3 to any thief, and it's impossible to do that for instance 4 or more, then this is our answer, right? We want to stay as far away as possible for the cell that is the closest. Now in general, when we have a grid, we want to use a BFS on that grid. That's probably the simplest way of thinking about most of those problems, and it's also easy to implement them. Also has another benefit. If you're used to implementing breadth first search on a grid, then you'll be fast at doing that, you won't make many mistakes. So that's also nice. You'll build confidence for yourself that you can solve those problems. Here we can, I think for every solution, it would be useful to first calculate the safeness that every cell gives. You can do that with our favorite BFS. If you don't know how, then you can think about it for a second. How to calculate for every cell what is the closest one to that cell. And the solution to that problem is to calculate those distances starting from every thief, but starting from all the thieves at the same time. Because every thief has the safeness of 0. Then every cell that still hasn't been calculated for its safeness and is adjacent to a thief has a safeness of 1. Again, every cell that has not been calculated but is adjacent to the cell with safeness 1 will have safeness 2, and so on. So essentially here we have safeness 0, so this is safeness 1, this is safeness 2, and so on, right? So that's simple. We can use BFS to calculate it. And we should do so, I think, for every solution. So that will be the first pre-processing step, and after that we can forget our original grid. Since I think it's a good idea to solve this problem without using anything more sophisticated than a BFS when it comes to algorithms, the key to doing that in a reasonable time is to notice that what we want to do is we want to maximize some factor. And we have this nice property that so let's say that this is the maximum good factor. And in this example, it will be equal to 2. It's impossible to do it in 3. It's impossible to do it with safeness 4, safeness 5, and so on. But it's possible to do it with safeness 1, safeness 0, and so on. It's, in this case, possible to do it with exactly those safenesses. We can also consider what is the maximum safeness factor such that we can use that, those or more, right? So if it's possible to solve this problem by getting a safeness of 2 or more. So then still the answer would be the same because it's impossible to get 3 or more, but it's possible to get 2 or more. When we have this nice situation, then we can find this point where it changes from all okay to all not okay by a binary search. It may seem scary at first to do a binary search on something that is not an array, on something abstract. Essentially, it's a binary search on the answer. But I assure you that it's very simple. This method is very general. Some problems it's possible to solve using this technique. Other problems that have nice linear time solutions can be, in a way, cheesed by using binary search on the answer. Some mathematical problems. So for instance, when there's an operation that you can do many times, like 10 to the 18 times, it's possible to solve it mathematically in linear time or just binary search on the number of steps. Anyway, it's a very useful technique. It's a technique that may be hard to come up with yourself until you see it. But then when you've seen it already, try to remember it, and you can utilize it to solve some problems, including this problem. You can just binary search on the value, because for the binary search on the value, the answer becomes, or the question you want to answer, becomes not what is the maximum safeness factor, but is it possible to achieve that safeness factor or more for any path? And in that case, we can just, for instance, if we're being asked to get a safeness factor of 1 or more, for us, every cell that has a safeness of 1 or more exists, every other cell doesn't exist, and we want to just connect the first cell to the last cell. And of course, it's possible. If we're asked for the number 3, so only cells that have safeness 3 exist, so this one, this one, this one, and this one, then it's impossible to reach them. Right? So that's very simple. We just have to check reachability, which we can do, of course, with a BFS. Now, the code is quite long, and there are some other solutions, so I also discuss some other solutions. Maybe some of them will be more intuitive for you, but I think they will utilize a bit more of either things specific to this very problem, because this solution is very general. It's just a BFS, then a binary search on the answer, which we can verify with another BFS, and that's it. But I'll talk about some other solutions, and then we'll see the code. So one simple way to solve this problem, and I think all the other ways, will utilize the fact that we essentially want to take all the cells, right, move to all the cells, but in order of highest safeness, right? So, because, yeah, that will be the way in which we can maximize the minimum safeness of any cell on our path. And in general, we can either use a priority queue, so do something similar to the Dijkstra algorithm, so that we remember every cell that we can visit, so we haven't visited yet, but we can visit. We have them ordered by their safeness decreasing, and we always, until we reach the lower left cell, we take them. Now, if that safeness is smaller than what we've seen previously, then, well, our answer will be always equal to, at most, what we've taken. So we have to reduce our answer. And then we can also update all the other cells that were now that are neighbors of that new cell we've added, add them to our priority queue, and we do that until we reach the final cell. And the smallest safeness that we've accepted in a cell that we've taken will be our answer. So that is a priority queue based solution. We can also utilize the fact that there aren't many Manhattan distances. The maximum Manhattan distance is about 2 times n, right? Because those cells have Manhattan distance of about n plus n, or exactly n plus n possibly, or n minus 1 plus n minus 1. And in that case, we can probably do something by maintaining, let's say, edges. So between 2 cells, we take that edge to be like the minimum safeness among those 2 cells. We can maintain them sorted by safeness, but in linear time. We just put them in buckets, and those buckets are safeness 0, safeness 1, safeness 2, and so on. And we can either then probably run a BFS that'll just, whenever we see a new cell as a neighbor, we just add it to the appropriate bucket, and then we take them out, take nodes out from the bucket that is possible to take them out from, because we still maintain the lowest safeness that we've seen previously. That may be possible, maybe not. One thing that I think is more likely to be possible is to just use find union, to use disjoint set union data structure. And in that case, we can start from we can go through all the safenesses from the largest safeness, and we can just union, so we can put together all the nodes that have at most that safeness, and after every step, going from the highest safeness possible downwards, we can see if the first and last cell are in the same connected component. And if not, then we just reduce our answer by 1, we connect some more cells together that are now able to be connected, and then we see if they are in the same connected component. So there are many solutions, but all of them are more specific to this problem, and all of them use things more sophisticated than a binary search and a BFS, because a BFS and binary search are very simple and basic algorithms, but very powerful, as you can see, that they are able to solve this problem. Okay, so now let's walk through the code. First, we start with the boilerplate, height, width, 4 directions. We'll have an auxiliary array, as I mentioned, that we'll use instead of our grid. So this is just the safeness of every cell. And we calculate it as we mentioned. So first we start with our queue by marking the safeness of every thief as 0 and appending it to our queue. So we have a multi-source BFS. nothing changes compared to a normal BFS. We'll maintain the number, the current layer number, so that we know what safeness to write to a new cell that we visit. Now, there are many ways of writing a BFS. I also think that in Python, since we can change a list or change a collection while iterating over it, then it's possible to write a BFS in an even shorter way, so you might think about it. But I like writing it like that. So we remember how many nodes are currently on the queue, because they will have the same answer. They consist of one layer of nodes, so they will have the same safeness. We go through all of them. We go through their neighbors. And now, if that neighbor was not visited yet, we mark their safeness and we add them to the queue. So that will simply transform our grid from the original grid to the grid where every cell knows its safeness. Okay, so that's fine. And now we'll binary search on the answer. The maximum answer is the maximum safeness of any cell on our grid. So in order to binary search, we will have to have a function that will verify for the suggested safeness, so for the candidate, if it's possible to reach from start to end while only using cells that have safeness that's at least equal to the candidate. So for instance, if the minimum safeness of the starting cell and the ending cell is already less than the candidate, the answer is false. If we can't reach the candidate, the answer is false. Otherwise, we just try to reach the candidate. So we have a two-dimensional array to mark what cells we've visited already. We start with 0, 0, and we just do a simple BFS now without calculating any distances. So for as long as the queue is not empty, we just take the new node, try to go in 4 directions. If it's inbounds, then we verify. Is safeness equal to at least our candidate answer? And if we haven't seen that node already, then if this is the end node, the answer is true. Otherwise, we just add it to the queue and keep searching. Very simple BFS that will verify if it's possible to use safeness of equal to at least candidate answer. And now we have to just binary search on that. Now many people write binary search as left bound, right bound, look at the middle, check the middle, then move some bounds. I of course write binary search in a different way, starting from the left and doing big jumps and then smaller jumps and smaller jumps to the right. So if this is so those are all the possible answers. I don't have to know that bound, so I don't care about that bound. And I just try to start in with this value, jump, then jump, but only half the length, and maybe it's possible, so I try to jump half the length again. It's impossible, so half of that's possible. Another one is not possible, this one is not possible, this one is possible, until we just get jumps of length 1, and then this is the answer. Alright, the solution is very simple to code, and it's very hard to make a mistake, because we start with answer 0, because in that case we know that 0 is always possible. We start with a jump, so we might as well just start with the maximum safeness plus 1 divided by 2, so the ceiling of half the maximum safeness. And we'll just keep jumping and jumping and jumping for as long as the jump is greater than 0, so it does something. The jump will be decreased by half at every step. We'll divide it by 2 at every step. And just for as long as possible to jump, that's either 0 times, 1 times, or 2 times, right? So not many, but we can just write while true. Now, if it's possible to make that jump, so answer plus jump, our new answer is okay. This is the function, okay. That verifies if it's possible. Then we just say, okay, now we know that it's possible to get that answer. So that's our current answer, and we start jumping from that position. So we started here, now we're here, and we jump forward. And if it's not possible, then we break, because now we want to reduce the jump. And if after the reduction, the jump is now 0, then we know that this is the last possible position where our OK is true. It's also, I think, easier to see that it is actually correct, because the jump will always be 1 at the end, so we'll jump by 1 to the right for as many times as necessary. It won't be many times, but we can be sure that we'll reach exactly the last portion. So I recommend that you write binary search like this. I think it's easier to not make a mistake. It's a cute way. You don't have to know the right bound exactly. So yeah, this is just the binary search on the answer. And finally, we just return the answer, and this is this problem solved.